Yeah, good morning. In the last session, I talked about the strength and toughness of the solid shell, because when the solidification is taking place, the strand which is for continuous casting, of course I am talking about, which is coming out of the mold and it's taking a different shape and finally becoming horizontal. So lot of strains are the shell is subjected to a lot of strains rather, yeah. The solid shell and the strand, they are undergoing a lot of strain. Now I have mentioned what are the sources of the strain. Solidifying shell is undergoing strain during and after solidification. During solidification also, and even beyond that there is a lot of strains. So what are those? First and foremost is the ferrostatic force from liquid during solidification. During solidification, ferrostatic force of the liquid which is present in the strand. Strand is having liquid, solid and the mushy zone. Three distinct zones are there. So the liquid which is present in the strand will give lot of ferrostatic force, will give some force on the solid shell. So this is important. Then of course there will be shrinkage during solidification. So in steel, there is a shrinkage when solidification takes place. So solidification taking place means there will be shrinkage. Now additionally there will be shrinkage from the transformation of delta to gamma. I have mentioned that for certain grades of chemistry, initially you will have delta, then you have gamma, and for certain grade of chemistry you have only gamma during solidification and beyond that. After solidification, for all chemistry of steel, different types of steel, you have only gamma, but for certain chemistry you have initially delta and then gamma. So what is important is for those chemistries, the transformation from delta to gamma, when is it taking place, to what extent is taking place, at what temperature region it is taking place, these are very important. So they might also add to the shrinkage value. So this is important. Then I have mentioned there is a mechanical strain due to bending and unbending of strand. In the last session I have discussed in detail that if there is bending of the strand, that means when from a vertical mold caster which had only vertical mold, straight mold, when the strand is coming out it is also vertical, straight. So it has to be first bent, otherwise it will continue to move only in vertical direction, which is not of much use. Finally it has to be made horizontal. So initially vertical strand you make it, you give it a bend. So during bending at the inner radius, shell at the inner radius will have certain strain. Shell at the outer radius will also have certain strain of different type. If it is the internal side is compressive, the outer area, shell at the outer area will have just the reverse of it, tensile. So again after certain time it has to be straightened, that means there has to be unbending. So initially during bending there is certain mechanical strain, during unbending you have just the reverse type of strain, again mechanical strain on the strand, both at the inner radius also at the outer radius. So mechanical strain during bending and unbending of strand, again we have to keep in mind, because this might cause formation of crack unless the shell has sufficient strength and toughness. Then there may be thermal strain during secondary cooling. We are cooling the strand surface with water or mist, so it will create thermal strain. So this is again important. So the solid shell, if it is delta or gamma, must have adequate strength and toughness at high temperature to withstand a different strain. This is important. By high temperature I mean the big range of temperature from 1400 to 600 degrees centigrade, because solidification only the start of the activity of continuous casting. After solidification is complete, the strand is again getting cooled in the secondary cooling zone by water or mist. So again the temperature of the strand will come down slowly, the internal portion of the strand will also come down slowly. So, at a different rate, surface is getting cooled relatively faster. So, whole temperature range, that means that when the solidification is starting to even as low as 600 degrees centigrade, this is quite low in temperature. So, what are the relative values of strength or toughness in the strand is important, because it should be adequate to resist the formation of crack. That is why it is important. Then I have given the concept of zero strength temperature, zero ductility temperature, and the liquid impenetrable temperature. So, and I have mentioned the zero strength temperature is around solid fraction of 0.7. Zero ductility temperature is around solid fraction of 1. That means around solidification complete, actual completion of solidification, actual solidus temperature is zero ductility temperature. And another important parameter is the liquid impenetrable temperature, is called LIT, which corresponds to around solid fraction of 0.9. So, this temperature region between LIT and ZDT, that means between the solid fraction of 0.9 to 1, that means towards the end of solidification, this region is really critical, because in this brittle temperature zone, if there is crack formation, liquid still cannot heal up, because the two dendrites are touching each other. That is why it is called liquid impenetrable temperature. Liquid cannot penetrate beyond this temperature in this zone of temperatures region. So, that is why the difference between LIT and ZDT, the temperature differential between this is, that means the solid fraction between 0.9 and 1 is in true sense the brittle temperature zone near actual solidus. So, solid fraction between 0.9 to 1, please remember this is really a matter of OD, we have to be careful about that. So, the temperature zone between LIT and TSA, liquid impenetrable temperature, and actual solidus is the real brittle temperature zone near actual solidus. Now, I have also mentioned that depending on the chemistry of the steel grade, two opposing forces are acting on solid shell. Two opposing forces are always acting, it depends on their value, their amplitude, which is again a consequence of the real chemistry of the steel. How the chemistry is affecting this? I have mentioned that chemistry affects the mode of solidification. That means how solidification is taking place, whether initially delta is forming, then when delta to gamma is forming, when solidification is getting completed, whether it is only through gamma when solidification is starting. Finally, it will be gamma, but initially whether delta is there, then at what temperature delta will transform to gamma, is it during solidification, at what stage of solidification, or lower than solidification, when solidification is complete, transformation from delta to gamma is taking place. These are all important issues, which issues related to chemistry, because these all depends on the chemistry. Carbon equivalent or carbon for plain carbon steel, and for stainless steel, as I mentioned earlier, the ratio of nickel equivalent by chromium equivalent. These factors will decide how the transformation will take place, number one. At what temperature transformation will take place, at what temperature solidification will be complete. Everything depends on chemistry. Number two, I have mentioned the role of microsegregation. Microsegregation is also affected by what are the alloying elements present in steel, and I have mentioned the two elements phosphorus and sulfur are very deleterious. Fortunately for sulfur, there is a savior element as known as manganese. Manganese combines with sulfur, forms manganese sulfide, and the deleterious effect of sulfur is taken care of. Unfortunately for phosphorus, there is no such savior element in liquid steel, in steel rather. So, phosphorus has to be kept at lower level, otherwise there will be too much of microsegregation, and the consequence is the actual solidus is suppressed or depressed, and if it comes down, the solidification temperature interval increases. If that happens, the consequence is the actual shell thickness is lower, less, and the mushy zone is more during solidification. So, the actual thickness of the solid shell is very important, the shell strength is very important, and then how much of transformation is taking place due to delta to gamma, where it is taking place is important. So, these factors, that means the chemistry influence these factors, and these factors in turn will influence what will be the solidification characteristic for a definite chemistry, for a particular chemistry. Let us see how it is happening. Two opposing forces are acting on solid shell during solidification. One is the ferrostatic force, which is pushing the solid shell towards the mold, away from the liquid. It is pushing towards the mold. So, this strain I have mentioned, if we call it SB, that means sticking or bulging, it is equal to the ferrostatic force divided by the sigma, that means the strength of the shell, and the square root, and not the square root, square of the actual shell thickness SA. So, these three factors are important. That is why I was mentioning strength of the shell is important, shell thickness is important. These two are a consequence of the chemistry I have mentioned. Whether delta or gamma will form, it depends on the chemistry, and the strength of the shell sigma depends on whether it is delta or gamma. Gamma has a strength, high temperature strength of about 5 times than delta ferrite. So, this is important, and this actual shell thickness is determined by, as I have mentioned many times, by microsegregation. So, if the microsegregation is more, the shell thickness is also less. So, the sticking or bulging strain can be found out from this relation. Another force, I have talked about the two opposing forces, one is ferrostatic, another is the shrinkage. Why shrinkage is taking place? It may take place due to solidification, it may take place due to cooling, take place due to transformation from delta ferrite to gamma. Now, the effect of all these three are, this shrinkage are basically to move the shell away from the mold towards the liquid. So, ferrostatic force pushing the solid shell towards the mold, away from the liquid. Here shrinkage is pushing the shell away from the mold and towards the liquid. That is why these two are opposing forces. So, which force is more for a particular chemistry is dictated by the relative values of SB and STH plus STR, that means thermal strain or transformation strain, summation of that, because both thermal and transformation strains are adding up to and causing shrinkage. So, shrinkage is due to solidification, cooling and transformation. Solidification and cooling basically you can find out due to the shrinkage of this temperature effect, and transformation is due to the effect from transformation from delta ferrite to gamma. So, the thermal strain and the transformation strain together have to be looked into. If SB, that means the bulging strain, is more than the summation of thermal and transformation strain which is causing shrinkage, then it is a sticking or bulging grade. That means that particular grade will have sticking and bulging tendency. But if the reverse is true, that means the shrinkage from the thermal as well as from the transformation together, this value, this summation is more than the strain of bulging. If the thermal shrinkage strain is more, then what is the consequence? That this will result in formation of surface depression. Shrinkage is more, so that means there will be surface depression. The solid shell will have some depression on the surface, and if the ferrostatic force is more, the strain due to ferrostatic force is more, then we have sticking or bulging tendency. This is very important. We should remember that all the steel, depending on their chemistry, can be subdivided into two basic categories depending on whether the bulging strain is more or the shrinkage strain is more. If the bulging strain is more, we call it a sticking or bulging grade. Those grades will have sticking and bulging tendency, inherently bulging and sticking tendency. And if the shrinkage strain is more, shrinkage due to both thermal as well as transformation. Transformation is also very important for certain chemistry. If the summation is more than the bulging strain, then the consequence is formation of surface depression. So, certain grades will have surface depression. So, the whole chemistry range can be subdivided into two broad categories of sticking and bulging tendency one, and the other one is depression tendency. These are inherent tendencies depending on the chemistry of the grades. Now, let us look at what is the effect of carbon, in normal low alloy steels. So, I have talked about the brittle temperature range during solidification, which is towards the end of the solidification, towards the final stage of solidification between solid fraction of 0.9 and solid fraction 1 between LIT and ZDT. So, now let us see with carbon how is it changing. If you look at this particular figure, we will find that initially during solidification there is liquid, then from liquid we have delta plus liquid or delta plus gamma plus liquid depending on what are the chemistry, or you may have here you may have liquid plus gamma only at high carbon or carbon equivalent. So, towards the end of solidification, this is the solidification complete line, that means Fs is 1, that means ZDT, this is that line. Solidification is starting at this line, this is the temperature is called liquidus temperature, and this is the actual solidus temperature, which is equivalent to ZDT, 0 ductility temperature. And a line has been drawn within this solidification range equivalent to nearly equivalent to around 0.9 solid fraction, which is LIT. So, what is the temperature? I have mentioned that this is the temperature range which is brittle. The temperature range between LIT and ZDT, temperature range between solid fraction of 0.9 and 1.0. We should be careful about this temperature region. Here also it is brittle, this temperature region, but as I have mentioned earlier, even if there is crack formation, liquid will go and heal those cracks, though the cracks cannot sustain, cracks will not remain. But if there is a crack formation in this brittle temperature region, those cracks cannot be healed, because then the liquid steel cannot penetrate in this temperature region, because the dendrites have started touching each other. So, towards the end of the solidification, this temperature region is the brittle temperature region, and if we have high strain in this region, we will have formation of crack. So, we have to be careful. Now, let us see with carbon how the solidification is taking place. When it is very low, that means say 0.5. So, initially it was delta solidification, and solidification is complete at that temperature. So, it is delta only solid. So, solidification is through delta. So, delta to gamma is not taking place during solidification, delta to gamma is taking place only at much lower temperature here. Okay. So, now let us come to this C1 temperature. What is C1? C1 is the intersection of this delta to gamma line, that means this line with ZDT line. This is. So, what is the situation here? If it exceeds this C1, if the carbon exceeds this C1, then this delta to gamma transformation, which is taking place here, delta to gamma is taking place here. So, if the temperature is if the carbon content is less than C1, as I was talking about say 0.5, then what happens, delta 2 gamma is transformation is not taking place during solidification. But above C1, delta 2 gamma has started forming towards the end of solidification. So, what is this this chemistry? C max. Here the delta 2 to gamma transformation which is taking place here is taking place entirely in the brittle temperature region, you see. And what is this temperature C2, say around 0.2? Beyond C2, delta 2 gamma, this was the delta 2 gamma line. Above this is delta plus liquid, here is delta plus gamma plus liquid. So, delta 2 gamma transformation is completed, delta 2 gamma transformation is completed above this brittle temperature region. Is it clear? The implication of C1, C max and C2, when carbon content is less than C1, say 0.05, delta to gamma transformation is taking place only after solidification is complete. During solidification, no delta to gamma transformation is there. Beyond 0.2% carbon, when it is more, delta to gamma transformation is taking place during solidification, but above this critical temperature, brittle temperature range. At Cmax, this delta to gamma is taking place entirely in the brittle temperature region. That is why this chemistry Cmax, we have to be very careful, because when delta to gamma transformation, I have told you it has some shrinkage. So, it is that shrinkage is taking place in the brittle temperature range. That means that strain due to shrinkage from delta to gamma transformation is taking place within this brittle temperature range. I have mentioned that we have to be careful about this brittle temperature range. If the transformation takes place less than or above this temperature range, we need not worry. But if this delta to gamma transformation is taking place within this brittle temperature range of solidification, it is a matter of worry. So, the significance of these three chemistries, please try to remember: C1 less than C1, say 0.05, 0.04 percentage of carbon, solidification is through delta, and delta to gamma is forming at temperature much lower than solidification. Above C2, that means around say 0.2, delta to gamma is complete above this brittle temperature range. At Cmax, this delta to gamma transformation, this is the delta to gamma transformation range, this is taking place entirely in the brittle temperature region. That is why this chemistry, which is around 0.1, is a matter of worry, because some people call this around 0.1% carbon as a peritectic chemistry, which is not true. Of course, peritectic range starts from 0.1 and goes up to 0.5, but this chemistry, that means around 0.1, is a matter of worry, because here the entire delta to gamma transformation is taking place in the brittle temperature region of solid fraction between 0.9 and 1, between LIT, liquid impenetrable temperature, and ZDT. This is the ZDT temperature. So, we have to be very careful about that. Now, let us see with carbon how the strain due to solidification, cooling and transformation, how they are changing. Here there is two components have been shown. Is a thermal. Thermal means basically is a summation of solidification and cooling, and another is this one, delta epsilon, delta strain due to delta to gamma transformation, this one. So, you will find that as I have shown here, between C1 and C2, this dotted line, you see the dotted line is maximum at C max. Why it is maximum? Because the entire delta to gamma transformation is taking place in this temperature, in brittle temperature region. So, this has been plotted having a maximum value at C max. C1 it is 0, C2 it is 0. That means less than C1 this particular transformation has no consequence, above C2 it is of no consequence because it is forming above this brittle temperature region. But within the brittle temperature region, this delta to gamma transformation is a matter of concern, I have told you, and the maximum is at a value near 0.1% carbon C max. So, if we add this with the thermal strain, if we add transformation strain with the thermal strain, the actual curve looks like this. This is the transformation strain dotted, this was the thermal strain, and when these two are added we get this one, this peaks. So, you just look at what is happening, say at C max or around 0.1 we have a very high strain. This transformation strain is adding to the thermal strain. So, we have a relatively very high strain around say 0.1% carbon. So, we have to be really worried about this chemistry, because what is happening here, along with the thermal strain, the transformation strain is acting in this temperature region, and which is, I have told you, is a brittle temperature region between LIT and ZDT, between the solid fraction of 0.9 and 1.0. So, as I have mentioned, the chemistry plays an important role. So, here also I am trying to show that with change in carbon percentage, what is happening to the different phases, what is happening to the solidification, what is happening to the delta to gamma transformation. Here, as I mentioned, at carbon concentration less than C1, total transformation, total solidification is through the delta mode. Delta to gamma transformation, this line, delta to gamma transformation takes place and starts and is completed only after solidification at a much lower temperature. Beyond 0.2% carbon, delta to gamma is taking place, and up to say 0.4 or 0.45, it is taking place during solidification, but above this critical temperature zone. So, less than C1 carbon, no, it is not a matter of worry. Above C2, again it is not a matter of worry, because this is taking place above this particular temperature, above this particular brittle temperature range. So, it is not a matter of worry, but beyond C1 and C2 we have to be very careful, particularly carbon concentration near C max, where the entire delta to gamma transformation, delta to gamma is starting here at around 0.9 solid fraction, and it is almost complete towards the end of solidification. That means the entire delta to gamma transformation, you just see what is happening here, the entire delta to gamma transformation is taking place within this brittle temperature range. Beyond this it is slowly decreasing, because it is the amount of transformation is coming down, and above C2, that means when carbon concentration is more than C2, it is 0%, that means delta to gamma is taking place above this brittle temperature region. So, the same thing has been shown here, some quantitative estimation has been done. So, actual strain values have been used. So, it can be seen that the strain level can increase double, you see, they increase double, say about 0.1. So, that means more than it is increasing at here, at this level it is around say 0.7 or 0.8, but at about C max it is increasing to almost 0.0018. So, that means from 0.008 it is increasing to 0.018. So, it is more than getting doubled because of this transformation, delta to gamma transformation. So, what I mentioned is the brittle temperature range during solidification, which is between solid fraction of 0.9 and 1, that means near the solidification complete region. This temperature is very important because this is the brittle temperature region. If there is a crack formation, liquid steel cannot reach the dendrite at the crack locations and heal up because dendrites are touching each other. So, there is no possibility of the liquid steel healing up the cracks forming on the dendrite surfaces. So, this is the temperature region. If there is lot of strain formation in this temperature region, there will be crack formation. So, it is a possibility of crack formation goes up for certain chemistry ranges between C1 and C2, and the maximum is at chemistry around Cmax, which is around slightly above 0.1. Now, this diagram is for a particular amount of manganese and silicon. So, this is basically carbon equivalent one should be interested in. Carbon, not carbon what percent is the carbon equivalent. If you change the manganese, silicon or other alloying elements, the actual diagram will change, but it qualitatively shows that for each chemistry of the steel you can draw it similar diagram and you can find out what is C1, Cmax and C2. That means you can find out what is the range of carbon within which there is a possibility of crack formation in this brittle temperature range, that means towards the end of solidification. The solidification crack formation, how is it varying with carbon, one can find out for any steel if you draw such diagrams. So, for this particular carbon range, that means between C1 and C2, you see the strain values are quite high. So, that means you have more of surface depression. So, this carbon range you have more of surface depression, that means between C1 and C2 you have surface depression and is the highest at Cmax. That is why this particular carbon range around 0.1, that means slightly less than 0.1 to maybe 0.15 or 0.16, normally people tell it is better to avoid that chemistry because this chemistry will have lot of surface depression on the cast product, whether it is bloom or billet or slab, you will find lot of surface depression. Why surface depression is forming? Because this delta to gamma transformation is taking place mostly in the brittle temperature region. You see the strain due to transformation is quite high in this temperature region, and this is forming in the brittle temperature region only. So, this is a real matter of worry while we are continuous casting this chemistry. So, this is called the so called depression grades, the so called peritectic grades. Basically it means the starting of the peritectic chemistry. Peritectic starts from 0.1 and it goes up to 0.5, but as we have shown here, the temperature, the chemistry range around say 0.08 or 0.7 to say around 1.7 or 1.8 is the real matter of concern, the real matter of worry. The actual values of C1, Cmax and C2 will depend on what are the other alloying elements present, but normally it is found around 0.1 only. That means the range may be from 0.7 to 0.16, it may be from 0.8 to maybe 0.17. So, basically what I am telling is around 0.1 only this chemistry is critical, which is known as depression grades, because the surface we have lot of depressions, and this chemistry has to be cast with lot of care. We have to use a particular amount of particular type of casting powder, which I have discussed earlier, because the heat transfer in the mold has to be controlled. I will touch these issues later on, but what I am trying to harp on is that chemistry plays a very important role in deciding what will be the type of solidification type or solidification characteristic of the grades. whether there will be depression or there will be sticking. You see this strain of depression, strain of shrinkage is quite high for this type of chemistry. You see here the strain of depression is relatively less for very low level of carbon. It is also relatively low when high amount of carbon. So, for low amount of carbon and relatively high amount of carbon, you do not have depression, you have rather sticking and bulging. But between C1 and C2 with the maximum tendency at Cmax, you have depression. So, you can make out from these figures how different chemistries, how different carbon content will behave, whether it will be depression grade, whether the characteristic of this grade will be depression or it will be sticking. These intrinsic behaviors, this either sticking or depression behavior depends on the chemistry. So, accordingly the casting parameters have to be selected to take care of these issues, so that the quality of the cast product is relatively good. Thank you very much.